Hello everyone, this is Mr. Bowman, and now that we are relative experts on graphing polynomial functions, we are going to move on to graphing rational functions. So before we start, we should probably define a rational function. A rational function is basically a quotient or one polynomial divided by another so long as the polynomial in the denominator is not equal to 0. So we're going to start out with about the simplest example of a rational function that we can, and that is the reciprocal function 1 over x. 1 is a polynomial of degree 0 in the numerator, and x is a polynomial of degree 1 in the denominator. And x is not equal to 0 except under certain circumstances. So we need to be thinking about domains of these functions. And we've talked about domains before. With polynomials, all you have to focus on for the domain is leaving out the values of x that make the denominator equal to 0. So the only value of x that makes f of x equal 1 over x equal to 0 is 0. So the domain of this polynomial is all real numbers except for 0. So in interval notation, our domain is from negative infinity to 0 or from 0 to infinity. Now, you may or may not know what this function looks like. But I'm going to graph this real quick for you, and the graph looks like this, and you can see we've got all kinds of asymptotes there. We've got a horizontal asymptote of y equals 0. We've got a vertical asymptote of x equals 0. So we can write down statements using limit notation to explain the behavior of the function or the graph near those asymptotes. So we're going to start out with the end behaviors, those behaviors as x goes towards positive and negative infinity. So if you recall, we were saying what happens as x approaches negative infinity, or what happens to y as x approaches negative infinity. So as you can see by looking at the graph, the limit as x approaches negative infinity of f of x is equal to 0. Or as x approaches negative infinity, y approaches 0. Similarly, we can see that the limit as x approaches positive infinity of f of x is also equal to 0. Now here's where it gets a little bit more complicated, and it's been a while since we've talked about this, but limits as x approaches vertical asymptotes. And what you see here in this function is that the behavior or the value of y approaches positive infinity on one side as we approach x equals 0, and negative infinity on the other side. So this is where we get into using left and right limits. So the limit as x approaches 0 from the negative direction, from the left-hand side of the function f of x, is equal to negative infinity. In other words, as x approaches 0 from the left, y approaches negative infinity. Similarly, as x approaches 0 from the positive direction, f of x, or y, approaches positive infinity. For the next example, we're going to take a look at a function that does not appear to be a rational function, but we are going to rewrite it as one polynomial divided by another by getting a common denominator. So you can see that the common denominator is x minus 1. So we would write this as 2 plus 4 times x minus 1, all divided by x minus 1, which would simplify to 4x minus 2 in the numerator over x minus 1 in the denominator. So we do have one polynomial divided by another. The domain, again, is all real numbers except for those values that make the denominator equal to 0. So you can see by inspection that x equal 1 would make the denominator equal to 0. So our domain is from negative infinity to positive 1, skip positive 1, 1 to positive infinity. Now, we need to graph this thing to figure out these limit statements. So what we're going to do is we're actually going to jump over to the calculator right now and do that. So what I'd like you to do is pause the video, put this function either in its original form or its simplified form into your graphing calculator, get a sketch of it, and get a graph of it, and put a sketch of that on this coordinate system you see in front of you. So a sketch of the function g of x looks like this. If you did not get this, please double check what you put in your calculator and keep trying until you do get that. Be careful to make sure that you have the entire numerator and entire denominator in parentheses when you do this. So our limit statements go like this. The limit as x approaches negative infinity of g of x is equal to positive 4. The limit as x approaches positive infinity of g of x is also equal to positive 4. The limit as x approaches positive 1 from the left-hand side of g of x is equal to negative infinity, and the limit as x approaches positive 1 from the positive direction of g of x is equal to positive infinity. To be perfectly clear about what we mean when we say end behavior and behavior near vertical asymptotes, I'm going to write a few things down here. So end behavior basically means what y or f of x approaches as x approaches plus or minus infinity. And the limit notation for that looks like this. The limit as x approaches negative infinity of f of x, and you state what that's equal to. The limit as x approaches positive infinity of f of x, and you state what that's equal to. For behavior around vertical asymptotes, we have to talk about approaching that vertical asymptote from the left and the right. So what that means is what y equals f of x approaches as x approaches a vertical asymptote we're going to call that VA for short, from the left, which we're going to use a minus sign for, or right, which we're going to use a plus sign for. And so our notation for that looks something like this. The limit as x approaches the value of that vertical asymptote, whatever it is, from the left of f of x. And the limit as x approaches the value of that vertical asymptote from the right of f of x. And it's going to come down to one of two things. Those limits from the left and the right for vertical asymptotes are either going to be positive or negative infinity. And we'll talk more about how you find those values shortly. So let's start our conversation about vertical asymptotes by talking about where they occur. Vertical asymptotes occur at the real zeros of the denominator, the values of x that make the denominator equal to 0, as long as they're real values of x, as long as they are not also zeros of the numerator. If they're zeros of the numerator and denominator at the same time, then we have something called a removable discontinuity. So let's take a look at this simple example. F of x is equal to x plus 3 over x minus 4. Let's start with the domain. The domain is all real values except for x equal 4, because that makes the denominator equal to 0, and we know we cannot divide by 0 when we have a fraction. So the domain is from negative infinity to positive 4, skip over positive 4, or from 4 to infinity. So we have a vertical asymptote at x equal 4, or where x minus 4 is equal to 0, which translates to x is equal to 4. That is a value of x that is a real 0 of the denominator that is not also a real 0 of the numerator. So how do we determine the behavior near a vertical asymptote? We are going to use something called a sign chart. And basically, as I told you a few minutes ago, the value of y near a vertical asymptote is going to approach positive infinity or negative infinity. So we're going to plug some numbers in on either side of our vertical asymptote for x and see what the sign of f of x is. If the sign of f of x is positive for values close to x equal 4, then we have a graph that is approaching positive infinity. If the sign of f of x is negative, then we have a graph that is approaching negative infinity. And we need to check both sides. So we're going to plug 4 into our sign chart. And let's pick a number close to 4, but slightly to the left of it. So for example, 3.9. Plug 3.9 into the numerator. You're going to have 3.9 plus 3, which is going to be positive. And plug it into the denominator, 3.9 minus 4, which is going to be negative. So a positive divided by a negative is negative. So we know our graph approaches negative infinity as x approaches 4 from the left-hand side. Now we're going to do the same thing for a value of x slightly larger than 4. So plug in x equal 4.1. 4.1 plus 3 is positive. 4.1 minus 4 is also positive, so the result is positive. So we now know how our graph behaves as x approaches 4 from the left and the right. What I'd like you to do now is pause the video, put this function into your calculator, graph it, and draw a graph over here on the right-hand side where it says function graph and limit statements. Your graph should look something like this. You should see a horizontal asymptote at y equal 1, and you should see a vertical asymptote at x equal 4. And so we're going to use limit notation to describe both the end behavior and the behavior near the vertical asymptote. Let's start with the end behavior. The limit as x approaches negative infinity of f of x is equal to positive 1. The limit as x approaches positive infinity of f of x is equal to positive 1 as well. The limit as x approaches 4 from the left-hand side, from the negative direction, of f of x is equal to negative infinity, and the limit as x approaches 4 from the positive direction of f of x is equal to positive infinity. For the next example, we're going to take a look at a polynomial that has 1 in the numerator but has a quadratic that is factorable in the denominator. So it's not real obvious initially what the values of x are that make, what the real values of x are that make the denominator equal to 0, but this polynomial is factorable. So we're going to factor it, x minus 6 and x plus 1. Now we can easily see the domain and what values of x make, what real values of x make the denominator equal to 0. So our domain is all real numbers except for -1 and +6. So -infinity to -1, -1 to +6, +6 to infinity. So all real numbers except for -1 and +6. Similarly, we know that x equal -1 and x equal +6 are our vertical asymptotes. Now we want to see the behavior near the vertical asymptotes. So we're going to make another one of our sign charts, except now we have two different vertical asymptotes. One at -1 and another one at +6. So let's start on the left-hand side of the vertical asymptote at -1 and pick a number slightly less than -1, like -1.1. So the numerator is always going to be positive, so we'll just write that down. -1.1 minus 6 is negative. -1.1 plus 1 is negative, so you have a positive divided by a positive, which gives you positive. Now, here's where you have to be really careful. Because you have two vertical asymptotes, one at -1 and one at +6, you need to check both a number close to -1 and a number close to +6, and I'll show you what I mean. So, a number close to -1 but slightly larger than -1 would be -0.9. Our numerator is positive always. -0.9 minus 6 is negative. -0.9 plus 1 is positive, so you have a negative times a positive. So you have a positive divided by a negative, which is a negative. Now here's why you need to check a number slightly less than +6, because it's possible that the function crosses the x-axis and changes signs between -1 and +6. So let's pick a number close to +6 and see what happens. Positive 5.9. We have a number positive in the numerator. Positive 5.9 minus 6 is negative. Positive 5.9 plus 1 is positive, so we have a negative times a positive, which is also negative. Now, in this case, if you were experienced with these rational functions, you could see that between -1 and +6, the function is never going to be equal to 0. So if we had noticed that ahead of time, we could have saved ourselves a little bit of work and only picked a number between -1 and +6 to do our sign chart. But we'll see some examples of that later. All right, last part of the sign chart, pick a number slightly larger than +6, +6.1. The numerator is always positive. 6.1 minus 6 is positive. 6.1 plus 1 is positive. Positive divided by a positive is positive. So now we know how our function behaves to the left and the right of our vertical asymptotes. I'd like you to pause the video again, put this function in its original form. Make sure you put the denominator in parentheses, put it in original form into your calculator, and sketch a graph of it to the right. All right, so in green is what the graph should look like, and we've got a bunch of limit statements to write. So let's take care of the end behaviors first. The limit as x approaches -infinity of f of x is equal to 0. The limit as x approaches +infinity of f of x is equal to 0. The limit as x approaches -1 from the left-hand side of f of x is equal to positive infinity. The limit as x approaches -1 from the right-hand side of f of x is equal to negative infinity. The limit as x approaches positive 6 from the left-hand side of f of x is equal to negative infinity, and the limit as x approaches positive 6 from the right-hand side of f of x is equal to positive infinity. And here you can see what I was talking about, where the graph does not cross the x-axis between -1 and positive 6. So we could have gotten away with checking just one value between -1 and positive 6 on our sign chart. And this is the part that I'm talking about right there.